Hi everyone, Augie Kennedy here with Super Awesome Calculus, and today we're finishing off Chapter 4, which was entitled by me, Everything is Derivative. So, with the chapter test we're going to be concluding our applications of differentiation, and before we get started we're going to go over very briefly the antiderivatives that we were going over yesterday. I gave you a problem that read as such: f double prime equals x, or f double prime of x equals 24x squared plus 2x plus 10. I said that f of 1 equals 5 and f prime of 1 is negative 3. I asked you to find f. So this is one of those situations where you're given the second derivative and you need to use that information to go back to the first derivative and then go to the initial function. So let's try that. We have f double prime of x. That doesn't seem to be that it's like it's going to be big enough. We have f double prime of x equals 24x squared plus 2x plus 10. Okay? Now, we learned that taking the antiderivative is basically just going backwards. It's what function would give that as its derivative. That's the question. We also, well, I'll write up other given information as it comes up to save room. We need f prime of x. So f prime of x, using the techniques that we learned that this is acquired by going 24x to the 2 plus 1, which would be cubed, over 2 plus 1, which is 3, plus 2x squared over 2, plus 10x plus c. Now, what we also know is that f prime of 0, or wait, it's going to be, no, f prime of 1 is going to be negative 3. So negative 3 is going to equal 24, just plugging in 1 into the derivative. 24x to the cubed over 3 is going to be 24 over 3, which is going to be 8. So 8 plus 2 to x to the 1 is 1, so 2 over 2 is 1. Plus 10 times 1 is 10, plus c. So we have c, we have 19 plus c equals negative 3, or c equals negative 22. So the final derivative that we have here, f prime x should equal 8x cubed plus x squared plus 10x minus 22. Alright, so we're getting further along. We're almost there. We're going for the original function now, f. So if we go from f prime x to f of x, and we apply the same strategy. That would be, you're going to get 8x to the 4th over 4 plus x cubed over 3 plus 10x squared over 2 minus 22x plus d. Alright, well, what do we know? First of all, let's rewrite f of x as something that's more simplified so we can reduce some of these fractions. F of x equals 8 divided by 4 is just 2. 2x to the 4th plus x cubed over 3 plus 10 divided by 2, 5x squared minus 22x plus d. Alright, that looks pretty good. But we also know that f of 1 is 5. So f of 1 equals 5 equals 2 times 1 to the 4th is 2 plus 1/3 plus 5 minus 22 plus d. Now, there's going to be some fairly complicated arithmetic here, but what you'll get is d equals 22 minus, yeah? No, here's what you're going to get. You're going to get d is going to come out to 59/3. Yeah, not exactly too glamorous, which leaves us with f of x equals 2x to the 4th plus x cubed over 3 plus 5x squared minus 22x plus 59/3. And there you have it. That's f of x. And that's an application of antiderivatives. So, now that we've got that out of the way, it's time... Whoops. It's time to take the test. So this test is going to be like the other tests that we've had. You're going to get a concept question, a true, false, and then 3 exercises. You're going to have a L'Hopital's rule question exercise. You're going to have a graphing exercise. The graphing equation that I'm giving you is a polynomial, but don't think that that's going to make it so easy. And finally, you're going to get an economics-based optimization question. Now, just to remind you of a couple things. You're going to need to know the demand function. You're going to need to know that the revenue function is x, r of x equals x times the demand function. All right? So, those are just some things that you'll need to know for the upcoming test. So if you're still a little unclear on that, there's a wealth of information online about how to find the demand function, p of x. And you might want to look at that. And if you're shaky on any of the other rules, go ahead and check those out and make sure you're solid on them before the test. All right, so that being said, enjoy taking it, and I'll be right here when we get back. Cheers. Hi there. All right, so I hope the test treated you fairly well. Let's go ahead and let's go over the answers, shall we? First, the first question was I asked you to state the first derivative test. Well, it depends how technical you wanted to get here. You should give yourself full credit if you've managed to get the gist of what we're going for. We assume that f is continuous, differentiable, and we assume that c is a critical number in f. Okay? So, if f prime, if the derivative goes from positive to negative at c, if it's going from positive to negative, we've got a local max at c. If f goes for f prime, the derivative goes from negative to positive at c, and you can visualize that, we have a local minimum at c. And if f prime does neither, no local min-max at c. That's the first derivative test. You can be as technical or untechnical as you like with it, as long as you understand that that's the test and that's what it does. All right, so that was the concept check question. Now we've got a true-false question that somehow is related to the concept check. I just want to make sure you were very firm on this. And that is, if f prime of x is less than 0 for an x between 1 and 6, then the original function is decreasing on open interval 1 to 6. True or false? Well, this is obviously true because as we learned, if the first derivative is negative, it's a decreasing function. If the first derivative is positive, the function will be increasing. Those are two things that we learned that we can find out through the first derivative test. Or through finding the first derivative, not through the first derivative test. Okay. Now, on to the exercises. So the first exercise I gave you was a L'Hopital's rule problem. I apologize again for not teaching it perhaps as well as I should have, but maybe I can make that up by demonstrating exactly what we were going to do here. Alright, so here's the exercise. The limit as x approaches infinity of x cubed times e to the negative x. Okay, first step, direct substitution. Always try it. If it works, you don't need to do L'Hopital's rule. You don't need to do algebraic manipulation. You're done. So, let's try it. That would be infinity cubed times e to the negative infinity, which is infinity times infinity. Not good. That's an indeterminate product. We can't use L'Hopital's rule on an indeterminate product. We can only use it on 0 over 0 or infinity over infinity. But as we learned, we can take a product, and by turning one of these into a reciprocal, we can turn the product into a quotient, algebraically. So let's do that. The obvious choice here is we have x cubed, but then we also have e to the negative x. Well, the reciprocal of e to the negative x is just going to be e to the x. So why don't we do that? Let's set this up as the limit as x approaches infinity of x cubed over e to the x. Alright, now let's try direct substitution, and we get infinity over infinity, and now we can use L'Hopital's rule. So, h. Using L'Hopital's rule, we differentiate the top and then the bottom. Not the quotient rule, just differentiate the numerator, differentiate the denominator, and see what happens. Well, we get, if we do that, 3x squared over e to the x. Using direct substitution, we realize we have infinity over infinity. So we can use L'Hopital's rule again. And we get 6x over e to the x. Direct substitution, infinity over infinity. Now, this is going to be a moment where if you got to this point, you might have seen where this was going. If you didn't get to that point, you probably gave up just a little bit too early. So we have the limit as x approaches infinity by that point of 6x over e to the x. Direct substitution, once again, we get infinity over infinity. But don't give up. Use L'Hopital's rule again. And if you do that, you'll realize that now we have the limit as x approaches infinity of 6 over e to the x. Well, we know what that is. That's 0. Because that's 6 over some huge number. That's good. That's pretty close to 0. So in fact, the limit of this function, x cubed times e to the negative x, at infinity is 0. And that's how to solve that question. Now, there's one more, or two more. Now we're up to the really fun exercises. We've got the graph. This is the graphing exercise. The function that I gave you to graph was y equals, I'm going to have to keep this somewhat small, x to the 4th minus 3x cubed plus 3x squared minus x. Okay, well the first thing you want to do is you want to ascertain what the domain of this function is. As you can see that there won't be any, there aren't going to be any places. It's a polynomial. It's going to be defined everywhere. So the domain is x is an element of all real numbers. So it's going to be defined from negative infinity to infinity. Alright, that's the first thing. Now we want to find the y-intercept. So let's take f of 0, and we get 0 minus 0 plus 0 minus 0. So obviously the y-intercept is going to be 0. Y int is 0. Okay, the x-intercepts, that doesn't look too easy to solve for x, so we're not going to worry about that for right now. What else? Is it going to be even or odd? Is there symmetry? Well, f of negative x is going to be negative x to the 4th minus 3 times negative x cubed plus 3 negative x squared plus x. And if you figure this out, you'll realize that not all of the signs change. Some do, some don't. So it's neither even nor odd. All right, so there's no symmetry. It's got a y-intercept at 0, and it's in all real numbers. What else? Well, we can look at it, and we can know that there are no asymptotes because it's defined everywhere, and we can take the limit at infinity, and we're going to get infinity. So, no asymptotes, good function to work with, which takes us right to the derivatives. So the first thing we're going to do is we're going to take y prime, first derivative. We get 4x cubed minus 9x squared plus 6x minus 1. Now, in the interest of time, I'm going to spare how to factor this out, but what you should get is when we're solving for the critical numbers of this derivative, you're going to get 0 equals x minus 1 squared times 4x minus 1. Which means that x is going to be critical at 1 and 1/4. So you're going to need to test those points. And if you test those points, you'll realize that f of x, or y, is increasing on negative, or on, no, it's going to be increasing on 1/4 to infinity, and f of x, or y, is decreasing on negative infinity to 1/4. So there's going to be a minimum. Yeah. Whoa. Gotta get my stuff in order. There's going to be a minimum at 1/4. Now, the fact that it's a minimum means that we're going to need to plug it right back into the equation. So we have the original equation, y equals x to the 4th minus 3x cubed plus 3x squared minus x. We plug 1/4 into there, and we realize that the local min happens at 1/4 negative 27 over 256. That's your local minimum. Not too easy to solve, is it? No. Alright, so let's do the second derivative. Y double prime is going to be 12x squared minus 18x plus 6, which is very easy to factor. Turns into 2x minus 1 times x minus 1, or x equals 1 or 1/2. We can see that it's going to, if you do the work here, you'll find that it's going to be concave down on 1/2 to 1. And it's going to be concave up on negative infinity to 1/2 and from 1 to infinity. Okay? That's the concavity. And then if you check 1/2 and 1/2 for inflection, 1/2 and 1 for your inflection points, plugging them into the original function, you're going to find that inflection points are at 1 and 0, right? Now, yeah, 1 and 0, and 1/2 and negative 1/16. So those are your inflection points. With all of that information now, you're ready to sketch the curve. And it should look kind of, sort of, like this. Down to here, you're going to get a nice little inflection to here, and then you're going to inflect again and go up to infinity. And that's basically what the curve should look like. And that's how we graph that function. Now, to the final question is the optimization question. And this one I expected to be fairly difficult, and I'm very impressed if you get this one. A hockey team plays in an arena with a seating capacity of 5,000 spectators. With the ticket price set at $12, average attendance at a game has been 11,000. A market survey indicates that for each dollar the price is lowered, average attendance will increase by 1,000. How should the owners of the team set the ticket price to maximize revenue on tickets and their sales? Well, this is kind of tough. First, we have to assign a variable. Let's let X equal the attendees. Attendance. Attendees, yeah. X is attendees. Well, we know that right now we have 1,000 people coming to the game. So any change in attendance, an increase in attendance is going to be X minus 11,000. Because we already have 11,000. If we've got 100 people increase, it's going to be 11,100 minus 11,000. So that's an increase in attendance. Also, we know that for each increase of 1,000 attendees, every dollar less, we get 1,000 more attendees, because it says the average attendance will increase by 1,000 for each dollar it's lowered. So what that's saying is that for every, I'm going to just call it delta X, it's going to be 1,000 X times $1. All right, so now we have P of X. P of X equals 12 minus 1 over 1,000. We got $12 times X minus 11,000. We got the price, 1 over 1,000 because of the increase, and we've got the change in attendance. That's our P of X. Now, we know that R of X is just X times P of X. So, R of X is X times P of X. Let's write P of X a little bit more neatly, shall we? All right, so P of X is really, if you reduce that, you're going to get 23 minus X over 1,000. Now, just looking at this, well, we'll get to that in a second. So that's P of X. R of X is going to be 23X minus X squared over 1,000. And we already know what to do here. Now we're just going to optimize by taking derivatives. So, R prime X equals 23 minus 2X over 1,000, or X over 500, equals 0. And you can figure out very easily that this is going to equal 0 at 23 over 5, X over 500 equals 23. And you can just multiply that through, and you can find that that means that X is going to equal 11,500. Okay, so we have X equals 11,500. Now the key observation to do here is go ahead and plug that back in to the original demand function, and we get P of 11,500 equals 23 minus 11,500 over 1,000, which is really just saying 23 minus 1150, 11.50. And what that means is that P of X is maximized to 23 minus 1150, which is 1150. So at $11.50, they maximize their revenue on ticket sales. Whew! All right. So that's the end of the test, and that's the end of chapter 4. Next time, we're going to learn about integration. There's only 2 chapters left in this course. This next one is going to be about how to integrate, and the chapter following that is going to be ways to use integration, much like we did with the derivatives. So with that being said, I'll see you next time, and thanks so much for joining me on Super Awesome Calculus. All right, take care, y'all.